Why are there conservation laws? Scientists delight in asking why questions. We want to know why apples fall from the trees, why coffee and cream mix but never unmix, why a fire goes out if you deprive it of oxygen. But it's a tricky business. We have to face up to the possibility that our why question bottom out with some ultimate answers with nowhere further to go than that's just the way it is. Happily, when it comes to conservation laws, we can do a bit better than that. It wasn't until the early 20th century but German mathematician Emmy Noether eventually proved a remarkable theorem relating conservation laws to symmetries of the laws of nature. The basic idea is straightforward. A symmetry is a transformation that you can do to a system that leaves its essential features unchanged. A circle that has a symmetry according to which it can be rotated by any angle around its center, a square, by contrast, is symmetric under rotation by 90 degrees or any multiple thereof. Noether's theorem states that every smooth continuous symmetry transformation of a system is associated with the conservation of some quantity. For example, the laws of physics overall are symmetric under the shifts in space. We can pick the system up and move it to somewhere else. And also under shifts in time, we can do an experiment, wait a little while and do it again. In either case, we should get the same answer before and after the shift. Noether's theorem relates the symmetries to conservation laws we already know. Invariance under spatial shifts lead to conservation of momentum, and invariance under temporal shift leads to conservation of energy. The number of different symmetries works out. There is one dimension of time and correspondingly a single conserved quantity, energy. But there are three dimensions of time, space, and we can translate separately in any one of those three directions. That's why momentum is a vector, which we can think of as having three components, one for each direction of space. There is also a symmetry according to which we can rotate the system around any of three independent axes. That gives rise to another conserved quantity, angular momentum. So this table, like symmetry, temporal shift, conserved quantity, energy. When the symmetry is spatial shift, the conserved quantity is momentum. And when the symmetry is rotation, conserved quantity is angular momentum. These symmetries, shifts in space, shifts in time, rotation, are all space-time symmetries, since they involve transforming the system in space and or time. In particle physics and quantum field theory, we have internal symmetries that rotate different parts of a quantum field into one another. It's these internal symmetries that are responsible for conservation of electric charge and a number of other particle properties. Subtlety arises when we remember that the laws of physics exhibit a certain symmetry, but the symmetry might be violated by the actual situation we find ourselves in. For example, our universe is expanding. Faraway galaxies are gradually moving away from one another as time passes. Consequently, there is a sense in which energy is not conserved in an expanding universe. The configuration of our universe isn't invariant under time shifts. Things used to be closer together, and in the future they will be farther apart. If we simply take the energy contained in all the different forms of matter that we know about, radiation, ordinary matter, dark energy, what have you, and add it all together, we get a number that is not constant over time. There are ways to try to fix this by defining an energy in the curvature of space-time itself, but those ways are not completely satisfying. There is nothing wrong with defining the total energy contained in a region of space as the sum of the energies of all the things within that region, and admitting that this number changes over time. All of which is to say, conservation laws are tricky. it is best to keep our wits about us. That's probably a lesson of broader applicability as we work our way deeper into the biggest ideas in the universe.